Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our look at aldehydes and ketones. We're going to begin looking at the preparation of aldehydes ketones. Specifically, first, we're going to look at the preparation of aldehydes. Aldehydes can be prepared from alcohols if the alcohol is a primary alcohol. So if we have a primary alcohol, we can react it to prepare an aldehyde. So if I have, for example, propanol, a primary alcohol, 1-propanol, I can actually prepare an aldehyde. But the problem is, if I use any oxidizing agent, I will oxidize not just to the aldehyde, but because the aldehyde is more easily oxidized than the alcohol, I will continue the oxidation process and go right through to the carboxylic acid. This is not desirable because, of course, this is aldehydes and ketones, and we want to prepare the aldehyde. So, how can we stop this? Well, we learned in alcohol chemistry that aldehydes are lower boiling because they don't have hydrogen bonding, so you certainly could set up a temperature of reaction above the boiling points of below the boiling point of alcohols and carboxylic acids, but above the boiling point of the aldehyde, and distill some of the aldehyde off. But it can be even more favored if we use a special oxidizing agent. If you use CrO3 in acid, you go right through the carboxylic acid. But if you use DOT2PY, it will stop at the aldehyde. Now, this reagent's often used in a solvent, of course, and a typical solvent would be methylene chloride, such as CH2Cl2. And if we use methylene chloride, we can stop at the aldehyde. Now, Py stands for pyridine. The pyridine actually interacts with the chromium, and you have two pyridines bound to the chromium, and this obviously interacts with chromium in such a way as it will oxidize the alcohol but not interact with the aldehyde. Okay, so if we use primary alcohols, and the important note is primary alcohols, you'll get an aldehyde. Note that if the OH was not in the primary position, if it was here in the secondary position, you do not get an aldehyde because the oxygen, if it became a C double bond O, would generate ketones. So that's why you have to have a primary alcohol. Well, we can oxidize alcohols, but we can also reduce acid chlorides. Acid chlorides are molecules which have a C double bond O, Cl. So let's use propanoyl chloride. You haven't learned this nomenclature, so don't worry. We're going to cover it when we get to carboxylic acid chemistry and the derivatives. But here's propanoyl chloride. It's an acid chloride, and we want to reduce this. And one of the first things that may pop into your head as a reducing agent is the use of molecules like lithium aluminum hydride. Okay, so Al and H4. And so aluminum hydride, aluminum is less electronegative than hydrogen, so hydrogen will have the delta minus. Effectively, each AlH4 can generate 4 H minuses. And then you could imagine H minus doing nucleophilic attack on the carbon here, delta plus. And then you get an O minus, and the O minus reform the pi bond and kick out chloride, and you would get an aldehyde. The problem with aluminum hydride, it's usually used in ether. It's so reactive that it won't stop. And by the time you treat it with water, you go beyond the aldehyde and you produce the alcohol. And so once again, we need a special reducing agent to stop at the aldehyde. So in other words, just as before, hitting this will go through the aldehyde. We will get H minus substituting, okay, substituting for the chloride. But it will go on and that should be an H. it will go on, another H minus will add, leaving an O minus, and then you throw in water, the O minus gets protonated, and you'll get to the alcohol. Well, this isn't desirable. We want the aldehyde. How can we stop at the aldehyde? We have to reduce the reactivity of the AlH4 minus. How can we do that? Well, one of the things we can do is we can take 3 tert-butyl alcohols and react it with the aluminum hydride. Now, tert-butyl alcohol is a sterically hindered alcohol, which means those bulky methyls somewhat shield the OH, but the aluminum hydride, source of H minus, the H minus is basic, and the 3 of the 4 H minuses can pull a proton off the 3 tert-butyl alcohols and combine to make H2 gas. So you will lose in this reaction 3, so minus 3 H2 gases that bubble out of solution. That will leave 1 H minus attached to the aluminum. But what else is attached? Well, you have your H attached to your aluminum. And then you have, of course, as you might guess, 3 tert-butyl groups. Now, what we do, of course, this is negatively charged still. So this is your lithium. So there's a negative charge on this, and you've got a lithium positive with it. We need to name this, of course. This is the LiAlH4 was lithium aluminum hydride. Lithium is a separate word. So lithium is one word, and then aluminum hydride was the next word. That's all one word as well. What is this guy called? It's a big word, so I'm going to have to start here. Lithium space tritert, because there's 3 tert-butoxy groups. Tritert-butoxy aluminum hydride. So tritert-butoxyaluminumhydride. Now, if we repeat our reaction on the acid chloride that we had up before, so here's my acid chloride. Instead of hitting it with LiAlH4, we hit it with Li square bracket HAl bracket C bracket CH3, 3 methyls attached to the carbon. Oops, I forgot my O. There is an O there. Okay, let's make room. Forgot my O. Let's do it again. O, C. Now 3 CH3s. And there's 3 of these, square brackets. This is usually an ether, okay? And that's a 1. And then 2 H2O, or acid sometimes. And if you use this guy will stop at the aldehyde. It doesn't go right through to the alcohol, and obviously we have to answer the question why. Well, there's a couple combined reasons for this. The first is my aluminum H4 could deliver up to 4 H minuses. The lithium Tritert-butoxyaluminumhydride only has one H minus that it can deliver. So there's one thing. We deliver less H minus per molecule. The second are these bulky tert-butoxy groups. They're so bulky they get in the way and they reduce the reactivity of the aluminum hydride. It's not nearly as reactive when it's tritert-butoxy because of steric hindrance. Steric hindrance is an effect that occurs when you have bulky groups around a site of attack or a site of reactivity, and it lowers the reactivity. So this is a much milder reducing agent, and because of that, yes, we can do 1H minus attack and get the aldehyde, but the reaction will stop. All right. So we can prepare aldehydes by oxidation of primary alcohols with CrO3.2py, a special reagent, or we can reduce acid chlorides. Again, we have to use a special reagent, lithium Tritert-butoxyaluminumhydride, which is a milder reducing agent. All right, how can we prepare ketones? Well, preparation of ketones can also go through oxidation of alcohol or reduction of acid chloride. Let's start with the oxidation of an alcohol. In this case, we have to use a secondary alcohol. And the reason being, a ketone has the C double bond O surrounded by carbon, so the OH that you're going to oxidize must be in the chain. So it could be a secondary. Also, you have to be able to generate a C double bond O. If it was a tertiary carbon, if we had another carbon here, you couldn't make a C double bond O because you'd have too many bonds to carbon. So secondary alcohols are perfectly set up to make a C double bond O, and that C double bond O will be in the middle of a chain generating a ketone. Now, when this happens, the oxidizing agent gives us a C double bond O. And the reagents that can be used, O in square brackets simply means oxidizing agent. We could use chromic acid, H2CrO4, which looks like a H2O plus a CrO3. We can use CrO3 and acid. We can use sodium dichromate, Na2Cr2O7, again in acid. Or we could use hot, KMnO4, potassium permanganate, the MnO4 minus molecule, in acid. All of these molecules, and these are just a few of the more common oxidizing agents that can be used to take a secondary alcohol to a carbonyl. Right? There are other reagents such as iodine and hot HNO3 that also could do this type of thing, known to oxidize. Now the secondary alcohol is required to make the ketone. If you use a primary alcohol, you're going to get an aldehyde or go right through to carboxylic acid, depending on whether you use CrO3.2py. Notice this reaction, we don't need the .2py because as far as you can go is the C double bond O. You can't oxidize this further unless you start breaking carbon-carbon bonds. All right, now what about acid chlorides? Well, can I make a ketone doing a substitution with a carbon minus? Well, the same problem we had with lithium aluminum hydride, in that it was too powerful and would take you right through to alcohol. If you take an acid chloride with a Grignard reagent like methyl magnesium bromide, you use something like this, followed by acid after. You do go through the ketone. You would put a methyl on in place of the ketone, in place of Cl, getting a ketone, but then the ketone gets attacked and you go right through to a tertiary alcohol. So this is not a prep that can work with these reagents. You can't stop with the one single addition of a methyl. Yields are not very nice. Yields are not very nice. So we don't want this. We want to make the ketone. What we want is to add only one methyl and get the C double bond O. And keep the C double bond O. How can we do this? Well, we have to take our Grignard. Let's go up here, rub some of these oxidizing agents off if we can. What we have to do is take our Grignard, and let's say it's going to be methyl, but it could be any alkyl, okay? Any alkyl group. The typical requirement for R is that R must equal a primary group, a methyl group, or an aromatic phenyl group. I'll use pH for benzene or phenyl. And if we take two Grignards, if your Grignard is of the right size, let's use chloride, and you react it with cadmium chloride, CdCl2, you can produce R2 cadmium, two alkyls attached to a cadmium, and an MgCl2. Now, of course, that would mean we'd get, if in this case, we'd have a dimethylcadmium or diethylcadmium. Let's use CH3 twice CD. Diethylcadmium. Now, this is often used in conjunction with acid or water. Okay, but often you'll just find it written over the arrow like this. And dimethylcadmium would add a methyl, the CH3 minus would go on. Cadmium is restricted in its size as to the groups you can go put around it. Clearly this is a problem if you want to put on something larger other than a primary or methyl or phenyl. Nevertheless, it works quite well. And the reason it works so well is the cadmium reagent is a much milder alkylating reagent than Grignard. Grignards are very powerful reagents, and cadmium reagents are milder. Nevertheless, what if I wanted to put on a secondary group? What if I wanted to make here, from the propanol chloride, I wanted to put an isopropyl on the other side. I wanted to make isopropyl, ethyl isopropyl ketone. Well, I can't use cadmium reagent because this restriction applies, and I would need to make a diisopropyl cadmium, and it can't form. A milder reagent than Grignard, though, are my copper reagents. Let's rub off the top here. I can take isopropyl bromide with two lithiums and make CH3 twice CHLI, isopropyl lithium. Okay. Now, if I take two of those, okay, so use 2, change this to 4, I get 2 of these. If I take 2 of these and react them with cuprous iodide, I can get lithium diisopropyl cuprate, right? So I can get CH3 twice, CH, 2 of these attached to my copper, Lithium diisopropyl-cuprate. Now, if I use lithium diisopropyl-cuprate, let's write that down here. Lithium diisopropyl-cuprate is a weaker alkylating agent than an alkylithium or Grignard, but it's stronger than dimethylcadmium. It's stronger than a cadmium reagent. So while cadmium reagents could be used at room temperature, these copper reagents can only be used at lower temperatures to limit the amount of alkylation. So 0 degrees Celsius to minus 78 degrees Celsius, somewhere in that temperature range, will give us the ketone with the isopropyl group on it. So, to use an acid chloride to make a ketone, if the ketone group you're going to add is primary methylphenyl, you can use a cadmium reagent. Cadmium reagents are prepared from the Grignard by reaction with cadmium dichloride. If, however, you need to put on a secondary group, you can use a copper reagent. That copper reagent is prepared from an alkyl lithium, and that lithium, of course, is from an alkyl halide reacted with lithium. But the copper reagent must be reacted at 0 degrees Celsius to minus 78 degrees Celsius, and you're required to know the temperature. The last methodology that we're going to look at for the preparation of a ketone is Friedel-Crafts acylation. Friedel-Crafts acylation. This is a reaction we covered last semester in the aromatics section. Friedel-Crafts acylation is the reaction again of an acid chloride, but with an aromatic ring. If, for example, you have a benzene and you react that with, perhaps, let's use our propanol chloride again. And you hit it with AlCl3. AlCl3 is your catalyst. I'm not going to put up the mechanism. We've covered this reaction through the benzene-onium ion before. We've looked at acylium ion formation. But what will happen is the Cl will be substituted for. You'll get the acylium ion, and the acylium ion is your electrophile that attacks the aromatic ring. And it puts a C double bond O, CH2, CH3. It makes a ketone. Now in the aromatic section, we took this ketone on and we reduced it. And we're going to actually look at some of this reduction chemistry a little later on. So there you have it. Similar reactivity to produce aldehydes and ketones, focusing on the chemistry of alcohols and acid chlorides. That brings us to the reactions, and we want to consider the reactivity of aldehydes and ketones. And of course, if we're going to consider the reactivity of aldehydes and ketones, in order to do this, we must examine the main functional group that will be reacting, and that is the carbonyl group. So here is the carbonyl, and I'm going to put on its oxygen. Put two lone pairs here, and I'm going to show the 2p orbitals that are overlapping to make my pi bond. So here's my side-to-side overlap of my 2p's. Bond angle is 120 degrees C, because 120 degrees C, 120 degrees, because of the sp squared hybridization. We have a polar covalent bond. The electrons are drawn towards the electronegative oxygen, so there's a delta minus here and a delta plus on carbon. So all these features combine to allow us to analyze the reactivity or influence reactivity, the planar structure, trigonal planar shape because of sp squared, Hybridization, its flatness, if you like, means it's more open and exposed to attack at the carbonyl. The pi bond, a diffuse source of electrons, electron-rich pi bond, available for electrophilic attack. The bond polarity puts a delta plus on carbon, allowing for nucleophiles to be attracted. And the non-bonding lone pairs of electrons to which we can attach electrophiles. So I'm going to put lone pair, non-bonding pairs, lone pairs of electrons. Okay, so lone pairs of electrons. All these four features combine to contribute to the observed reactivity. And we can check off the pi bond and the electrons as favoring electrophilic attack or attracting electrophiles. But bond polarity, delta plus on carbon, would attract nucleophiles. So we need to take a look at this and close look at the molecule and try to determine which, if any, actually influences the chemistry. So let's consider the reactivity in a little more detail and consider electrophilic versus nucleophilic reactivity. The two competing reaction paths would appear like this. Reaction with an electrophile, E+, could be envisaged as giving us this type of product. Likewise, we could envisage nucleophilic attack going for the delta plus on the carbon caused by the polar bond, the electronegative oxygen, withdrawing electrons. So nucleophile, if you like, minus could attack the carbonyl at carbon. Nucleophile binds to carbon, generating O minus. Now, electrophilic addition leads to a less stable product because it puts a positive charge on the electronegative oxygen. This would be considered reversible in that the electrophile would most likely come right back off. As a result of its instability, this is less likely to lead to a permanent product. Nucleophilic attack, on the other hand, can lead to an alkoxide. Oxygen being electronegative would help stabilize the negative charge. This would be a more stable product. Having said that, you should note that electrophilic attack would, by putting the positive charge temporarily on oxygen, would make oxygen more electronegative, more delta minus here, as it sucks electrons for carbon. That would put more delta plus. Attaching an electrophile to the oxygen might make carbon more susceptible to nucleophilic attack. That is, this bottom reaction might be sped up if we already had an electrophile attached here. And what electrophile am I thinking of? Of course, I'm thinking of H+. If we had added H+ first, this E would have been H, and I would have generated an alcohol with the attack of my nucleophile. So the electrophile attack may assist or favor the nucleophilic attack because I can draw a resonance structure. which would give me this. And I have a carbocation then, a resonance stabilized carbocation. And then the nucleophile attacks here. So effectively, if you like, because the carbon is more electropositive than it was, having the electrophile attached to oxygen, the nucleophilic attack is increased. It's assisted by the electrophile. Under acidic conditions, aldehydes and ketones can react with even weaker nucleophiles because you increase the positive charge on carbon. So a nucleophile could be even weaker. However, because it is the main attack is nucleophilic, we get what is called nucleophilic addition. This nucleophilic addition is often called nucleophilic acyl addition because you're adding to C double bond O, nucleophilic addition, an RC double bond O group. Because you're adding to that, you're adding to an acyl group here. It's often called acyl may be inserted here, but we'll stick with nucleophilic addition. One factor we want to consider is the relative rate, okay? If nucleophilic addition is the main reaction pathway that's assisted sometimes in acid, who reacts faster, aldehydes or ketones? In order to understand this, we have to look at the structure of the ketone, the typical ketone, versus the typical aldehyde. In terms of relative reactivity, we have two factors that will make ketones react slower, or slower to react than the corresponding aldehyde. The aldehyde reacts faster. All right. The first one is inductive. Oh, I've heard of this before. Inductive electron donation. You see, what attracts a nucleophile to the carbon? Well, it's the delta plus on the carbon. And the delta plus on the aldehyde is going to be larger than the delta plus on the ketone. Why? See, carbon is bigger. R groups are carbon. Carbon is bigger than H, more polarizable, pushes electrons through its sigma bond more easily. This inductive donation will reduce the size of the positive. I've exaggerated it with my deltas. But the point is, inductive electron donation from carbons reduce the size of the delta plus more than when you only have one carbon on the chain, which can donate electrons. Hydrogen doesn't do this very well. The net result is delta plus is bigger in an aldehyde. It's the delta plus that attracts the nucleophile. Nucleophile will come in faster in a larger delta plus. So inductive electron donation is the first factor. The second factor has to do with steric effects. Okay? Steric effects. Steric effects. Now, the steric effects are simply the size of the organic groups. Hydrogen is very small. The larger R groups, if they're methyl, ethyl, tert, butyl, much larger than hydrogen, will obscure the attack on the carbon. This, if you like, steric hindrance around the carbon will slow down the attack. Slowdown of attack will lead to, of course, slower reaction rates. So these two factors combine to make aldehydes typically react faster than ketones. Okay. Well, what we're going to do next is begin to take a look at some of the reactions that aldehydes and ketones can undergo. And let's begin with two reactions that are probably the simplest, and that is the reaction of aldehydes and ketones with water and alcohols. So let's begin with the reaction with water. Okay. When you react with water, water acts as a nucleophile. Let's try it with this aldehyde. So if we react with water, water initially will attack. So if I look at the initial attack, I'll get something that looks like this. If I was to do it in neutral conditions, I would get an O minus, and I'd get water down here adding. Now clearly this is going to be reversible. So probably should at this stage have an equilibrium arrow here. Now I can lose a proton. Which would give me this. And then I can add a proton. And if I add a proton, I will get this. Now what I've formed looks like a 1,1 diol. We covered alcohol chemistry last semester, and if you do go back and look in your notes, you will see that there are no examples of 1,1 diols that are reported. In actual fact, 1,1 diols, because of this equilibrium and the ability to eliminate water, typically shift back to the carbonyl, forming the aldehyde. If this H was a carbon, it would be a ketone. And so 1,1 diols are typically less stable. Very difficult to make 1,1 diols. 1,1 diols have the two alcohol groups located geminal to each other. Geminal means the two OHs are off the same carbon. However, this molecule, referred to as chloral hydrate, two words, chloral hydrate, is one of the few geminal hydroxy systems that is stable. It's suspected that the three chlorines, being so electronegative, they withdraw electrons from this carbon, putting a big delta plus. And so that withdraws electrons, increasing the delta plus on this carbon, allowing it to increase the nucleophilicity of the water. Okay, so that water, if you like, the delta plus on carbon is so much larger that it favors the water attacking and it shifts the equilibrium more to the right. So putting a very electronegative group has helped stabilize the chloralhydrate. Right? So in part, it's due to the greater electrophilicity of the carbonyl group that results from the presence of the highly electron withdrawing trichlorocarbon. The reaction with alcohols is a reaction that we have looked at in carbohydrate chemistry. The reaction with alcohols, with an aldehyde, for example, if you react it with, say, methanol in anhydrous HCl, so we can use acid to speed up the reaction, we will get a molecule that looks like this. And this functional group is referred to as a hemiacetal. And if we continue the reaction, methanol again, with anhydrous HCl, we will substitute for the OH and produce what is called a full acetal. Now, acetal chemistry was very important to carbohydrate chemistry, so you are familiar with this, having already covered it. Let me just say, okay, in fact, I'm going to go through and change my colors a bit. I'm going to label this H, make it black so it stands out. If the black H is replaced with a carbon, we have a ketone. If we do the same reaction on a ketone, the product with the OH on it is a hemiketal, and the final product is referred to as a ketal. So the hemiacetal, when you have two OCH3s, has become an acetal. However, that black H is replaced with a carbon-bearing group. You have hemiketal and full ketals. Now, there are two things that are very important in this reaction process, and that is being able to identify when you have these functional groups, hemiacetal and acetal. And secondly, the mechanism of formation. So we're going to look at both of these right now. Suffice to say that whether it's a hemiacetal-acetal or a hemiketal-ketal, these reactions are reversible, and the equilibrium typically will lie to the left, to the C double bond O. Just like 1,1 diols, geminal OH groups, a geminal methoxy in OH or a geminal 2 dimethoxys off the same are not stable. It's a challenge to get these, and you have to use special conditions, hence the anhydrous on HCl. And when we look at the mechanism, we'll see why this is the case. So it would be nice if we could come up with a set of rules that very quickly allow us to identify whether we have a hemiacetal, an acetal, a hemiketal, or a ketal. And the rules are as follows. 1, in order to distinguish between the functional groups to be classified as hemiacetal, hemiacetal, acetal, hemiketal, ketal, the carbon atom in question must be sp cubed, Okay, and must be only singly bonded. Okay, so that goes with sp cubed. It's singly bonded to other atoms. Singly bonded to other atoms. Okay, and two atoms are carbon. And two atoms are oxygen. In other words, the single bonds, the four single bonds in sp cubed, two must be oxygen. And you see that these, what I've drawn above, hemiacetal and acetal, meet that condition. Rule 2 is to identify whether you're hemi or not. In order to be hemi, the carbon atom in question must have an OH group. You must have an OH. If you have an OH, one of those two atoms is an OH, you're hemi. And only one can be. Otherwise, you're in the hydrate series. So, if there is one OH, then you're in the hemi category. To determine whether you're ketal or acetal, right, you look for, to be in the acetal family, that is hemi acetal or full acetal, the carbon in question must have an H. If there's an H off of it, you're acetal or hemiacetal. You have to check rule 2 to sort that out. If, however, there is no H, then you're in the ketal or hemiketal family. There's no H attached to the carbon. Okay, so let's check this out and just do a couple examples. Suppose I've got a complicated ring system like this, and I've got an OH. This goes back to carbohydrates. You've seen this type of thing before. Lots of alcohols and a sugar. Here's our link to a carbohydrate. Looks like we've got a glucose here. OH is down, which means right is below. It's to the right. This is alpha-D-glucopyranose. Does this have any bearing on hemiacetal, hemiketal, ketal-acetal chemistry? Well, if I look at the carbons, let's start this one. This carbon has an oxygen, but it's only one oxygen. It's sp cubed. This carbon only has one oxygen. This carbon only has one oxygen. This carbon only has one oxygen. But this carbon, okay, has carbons, okay, has a carbon. By the way, I said two carbons or two oxygens. It really should have been two oxygens, a carbon, or possibly a hydrogen. This could be a carbon. It may not be. So note that correction or that change to previous rules. The rule number 1, to be in this functional group, you must be sp cubed, 4 single bonds, 2 oxygens bound to it. The other bonds could be decarbon or hydrogen. Okay, so while we clearly have 2 oxygens, it's sp cubed, we have a carbon and hydrogen. So this functional group right here would fit into those categories. The 4 possible categories are hemiacetal, hemiketal, acetal, ketal. Rule 2 states to be hemi, there must be an OH. Well, looky here, there's an OH, so this guy is hemi. And Rule 3 states if there's an H bound to a carbon, it's in the acetal family. So what have we got? This is a hemi-acetal. Okay. Now we can look at another sugar. And so Does this type of sugar have any of that chemistry? Well, again, I could look at this carbon as 1 O. This carbon's sp cubed, it only has 1 O, 1 O, 1 O. But this guy, right here. Oxygen, two oxygens. Carbon, two carbons. But it has two oxygens, it's sp cubed. Clearly, this guy, this fragment right here, is a functional group that fits in this family. And what kind is it? Well, we have no H's attached, or we have an OH, so that makes it hemi. We have no H's attached, so it's a hemiketal. To make it a full ketal, all I'd have to do is change this OH to a CH3. Now it becomes a full ketal. This molecule would be methyl. If you remember your sugars, I believe it is alpha D fructofuranoside. Alpha D fructofuranoside. So some examples for identification. Well, that's easy enough, and there are a wide range of structures for you to practice in your problem sets. Let's take a look at the mechanism of formation to see if we can understand what conditions we need to form these less stable functional groups or less favored functional groups. Let's start from the aldehyde. Okay. Note, again, if we used a ketone, we'd get hemiketals and ketals, and I would only have to change this H, put a methyl there, for example. Well, clearly we're reacting, and we're going to use methanol. We're going to react with anhydrous HCl, so that means there's H plus around. So I'm going to add some H plus. And one of the things H plus can do as an electrophile, it's reversible. It can protonate the C double bond O. And that leaves this guy. It's a positive. Okay, and I have an H here. And so I can draw the resonance structure, how the electrophile enhances the availability of the carbon to its nucleophilic attack, increase the carbon's electrophilicity, increase its plus, if you like, by resonance. So you get this carbocation. And I certainly can attack that with methanol. Now, in acid, methanol will attack. I'll get RCOH, H. It still has its proton on, and a lot of students forget this. So there's going to be a deprotonation step. Don't leave out the deprotonation step. It's important. And so minus H plus. And you get to this guy, RCOH, H, OCH3. And we produce the hemiacetal. Now note, if this H right here was a carbon, what functional group would have been? It would have been a hemiketal. So the mechanism is exactly the same, whether you're going from an aldehyde to a hemiacetal or a ketone to a hemiketal. The reaction can continue, however. Reaction with acid again, more acid. We'll protonate the OH group. And then we'll get minus H2O. Kick out water. That will generate a carbocation. Now this carbocation, of course, is resonance stabilized. So this can dump in. And we can draw that here. And so it's susceptible to attack by methanol, because you're in methanol solvent. Don't forget, though, the methanol still have its proton attached. So there's a positive charge. And minus H plus will generate our full acetal. Again, if we had used a ketone originally, this H would be a carbon. If that H was a carbon, we'd have a full ketal here. Okay, that's the overall mechanism. Now, what conditions are we employing to help favor the formation of these? Well, one of the things we're doing is using anhydrous HCl. That is HCl dissolved in methanol that has no water. What this will do is facilitate the loss of water, but help prevent the equilibrium going back. You see, if there's no water around, once water departs, the probability of water colliding again and taking us backwards is less likely, because methanol solvents around it will continue to drive the reaction towards the acetal. Also, you'll notice to go backwards from either the acetal, the first step is plus H plus, to go back this way, or to go back from the acetal, you'd have to add H plus. And because of this, if we want to reduce the amount of H plus available, we can have the acetal or hemiacetal dissolved in base. If base is around, these guys are stable. So stable in base. So once you get them, once you form these molecules, the hemiacetal or the acetal, they're known to be more stable in base. Otherwise, if there's any water around, you'll drive the equilibrium back to the carbonyl. All right. So, if you like, let's just circle those so they're clear. This step right here, going backwards requires acid. And that's why it's stable in base. If there's base, there's no H plus to make this step go backwards. And so hemiacetal would be stable in base solution. Likewise, over here, the step going back, this guy, is plus H plus. Well, to have H plus around, you can't be in hydroxide. This concentration of H plus is too small, so that reaction won't happen. So going backwards, again, the acetal will be stable in base. Now, one interesting thing for discussion, of course, is the usefulness of acetals and ketals. And let's look at an example of the functionality they can serve outside of biochemistry, where they're found in the carbohydrates. Acetal-ketal chemistry is an extremely powerful tool to synthetic chemists. It can be used to control site of attack in chemical reactions. For example, suppose I want, let's go back to blue. Suppose I have this molecule. An alpha-beta unsaturated aldehyde. Now, I can oxidize this molecule in the presence of KMnO4. If you remember your alkene chemistry, if you use KMnO4, cold, dilute, in base, you could get syn addition and make a diol. You can make CH2OH. CHOH. The problem with this reaction, though, is you will not retain your aldehyde group, which may not be a problem if you want the carboxylic acid, but we know aldehydes are very easily oxidized, and hence it is highly probable that the aldehyde group would also get oxidized to the carboxylic acid. However, what if you wanted the diol and not the carboxylic acid? You wanted to retain the aldehyde. What could you do? Well, you could take this molecule and you could react it with a diol. Okay? Ethylene glycol. And of course, you don't have to use ethylene glycol. You could do methanol and add 2 methanol groups. It's just ethylene glycol is commonly used with anhydrous HCl. If you do this reaction, you will add 1 O and get a water and get the hemiacetal. And then protonate the water, kick the water out. And this guy, the other O, will wrap around and attack. And you'll get the full acetal. It will go through. And you'll get an oxygen, CH2, CH2, oxygen, and it'll bind here, and you have the H. You will get a full acetal. Now, this acetal is stable in base. And acetals are resilient to oxidation. They don't react, neither do hemiacetals. So if you like, both ends of the alcohol undergo the mechanism that we showed previously. Notice to go to the hemiacetal took 1 methanol. To go to full acetal it took a second methanol. Well, effectively our 2 OHs are on the same molecule and it wraps around, and that's a 5-membered ring. It's not too strained. And so if we now hit this with KMnO4, cold, dilute, the presence of hydroxide, full acetal is stable in base. We're in base. So we'll get the diols. We can work this up. Isolate the material with the 2 OHs on. And it will have a full acetal on it. Now, what did you learn? You learned that full acetals are stable in base. But if you throw an acid, they revert. Acid and water will revert them back to the carbonyl. So in a second step, we just throw H3O plus at this. You'll get back the ethylene glycol. And you'll get your CH2OH, CH2OH, C double bond O, H, plus of course the ethylene glycol. And you were able to put the 2 OHs, oops, that should be 1 H there, the 2 OHs on without oxidizing the C double bond O. The ethylene glycol became what we called a protecting group. A protecting group. A group that could be put on temporarily, protect a functional group from reaction, and then easily removed. Protecting groups are important in organic chemistry and often used, and acetals and ketals represent a major type of protecting group. So This hemiacetal-acetal chemistry is not just important in biochemistry and carbohydrates, but it's extremely important, but it also can be very useful to the synthetic chemist. And you should note this example. Okay, well that's enough for now. Reactivity of aldehydes and ketones will continue. There's a lot to look at, and we've just started. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.